No more fun.
Alrighty, here we go. 8.1. Let's do this. Sequences and series. So we're going to figure out basically what is a sequence and what is a series, and use the notation to write them. Use factorial notation, summation notation, and actually find some sums of partial series and infinite series. Um, so let's start right in. Um, in mathematics, the word sequence is used in much the same way that it is just in the way that we speak. Saying that a collection is listed in sequence means that it's in order. So that it has a first member, second member, third member, so on. Mathematically, you can think of a sequence kind of as a function. There are different types of sequences, just like there are different types of functions, but it consists of a set of positive integers. All right, so instead of using function notation, we just write using subscripts. So something like a sub 1 would be the first term of a sequence. A sub 2 would indicate the second term of the sequence. A sub 3 would indicate the third term. A sub 4 the fourth term, and so on, so on, so on, so on, all the way to a sub n, which would indicate the nth term, or in general, we would consider to be the last one. Um, so this particular sequence will consist of n integers, and is considered to be a finite sequence because it does end at some particular place. Sometimes we'll start the sequence with a sub 0, only when indicated though. So in general, we'll start with a sub 1 as the first term, but sometimes it might indicate that a sub 0 should be your first term. Just be on the lookout for that. Alright, so let's try and write the first four terms of the sequence. So it's a very, very simple process. You're just saying the first term would be a sub 1, which would equal 3 times 1, because n is 1 in this case, minus 2. So what am I getting there? I'm getting 3 minus 2, which is simply 1. And then I have a sub 2 here. A sub 2 will be 3 times 2 this time, and then minus 2, so that's 6 minus 2, which is 4. And the third term will be 3 times 3, 9 minus 2, which is 7. And the last one, a sub 4, which would be 3 times 4 minus 2. So we get 12 minus 2, which is 10. So here, right here on the right side, are my first four terms of the sequence given by this particular expression. Simple enough, right? Now let's move on to the next one. Again, we start with a sub 1 as my first term. 3 plus negative 1 raised to the n. Alright, so this one's going to be slightly different because we have the n value in the exponent, but still not too bad. So I get 3 plus, and then negative 1 to the first power. This n is a 1 the first time. So negative 1 to the first is negative 1, so 3 minus 1 equals 2. A sub 2 will equal 3 plus negative 1 raised to the second power. Now a negative raised to an even power becomes a positive, and since it's a 1, it's simply just a positive 1. 3 plus 1, 4. A sub 3 equals 3 plus negative 1 raised to the third power. Now this negative 1 is being raised to an odd power, which means it's going to again turn back to a negative 1. So 3 minus 1, 2. And my last term, I bet you can probably figure it out before we even write it in. Negative 1 to the fourth, and that brings us back to a 4. So here are my first four terms of this sequence. So as you can see, we have two very, very different sequences. We have one that looks very much like a linear equation, with the way that it's increasing every time by a specific amount. And then over here, we have something that's oscillating between 2 and 4. So it looks very, very different, but both considered to be sequences. Now let's look at factorial notation. Hopefully at this point everyone's used a factorial before, maybe in combinatorics, first year of Algebra 1, or maybe in geometry, logic, or something like that. Basically what it is, if I have some number with a factorial, which is the exclamation point, it's all of the previous integers leading up to that number multiplied together. Right? So something like 3 factorial would have been 1 times 2 times 3. Something like n factorial, just some number, would be 1 times 2 times 3 times 4, all the way up to the number that came directly before it, times n. And we have our special case where 0 factorial is defined as equaling 1. Yes, it's simply just a special case. It's just something that we need to remember whenever we are trying to evaluate a 0 factorial, which we will do here. We're going to have a different sequence this time, one that involves factorials, and I want to find the first 5 terms of it. And another little thing that we throw in here is that we want to begin with n equals 0. So my first term will be a sub 0. Alrighty, so that tells me that I need 2 to the 0 power over 0 factorial. Cool. Now, if I can remember from before, 2 to the 0, anything raised to the 0 power is simply a 1, and 0 factorial, as we mentioned just on the last slide, is a 1. So, altogether, that equals 1. Then I move on to my next one. My next one says a sub 1, which equals 2 to the first over 1 factorial. So now I need to ask myself, what is 2 to the first? Well, 2 to the first is simply a 2, and 1 factorial is simply a 1. When I simplify, 2. Now my third term, which is a sub 2, is going to be 3. Oops, sorry. Still a 2, but it's raised to the second. 2 to the second. Actually, I'm just going to erase that. Try that over again. Alright, my third term, a sub 2, which is 2 to the second over 2 factorial. And 2 to the second, as we all know, is a quattro. And a quattro over 2 factorial. 2 factorial is simply 2 times 1, which is 2. And when I divide, I get a 2. My fourth term, a sub 3, will be 2 to the third over 3 factorial. 2 to the third is a nice, beautiful ocho. And 3 factorial is 3 times 2 times 1, which is 6. 8 over 6 reduces down to 4 over 3. And my last one, my fifth term, a sub 4, is 2 to the fourth over 4 factorial. Now 2 to the fourth is a nice 16, and 4 factorial is 1 times 2 times 3 times 4, which is a 24. Simplified down gets me 2 thirds. So we have a very interesting sequence going on here. 1, 2, 2, 4 over 3, 2 over 3. Very, very different from the ones we looked at on the last page. Okay, so now that we've understood basically how to take the expression of a sequence and turn it into the numerics of each individual term, let's look at summation and summation notation. So sometimes what we want to do is we want to take all of the terms of a sequence and bring them together and add them up for either a partial sum, which would be, just say add the first 5 terms, or for an infinite sum, which we'll look at later. And when we do that, we use something called sigma or summation notation. Sigma notation simply because it's using this Greek letter sigma, and summation notation because that is what we're doing. We're summing together all the different terms. So there's a couple different pieces here that we want to look at. The first is this right here on the bottom, where it says I equals 1. I is kind of the general variable for when we use summation notation. It's the variable that we're going to continually substitute into the equation as for each individual term. And the bottom number here is the index. The index tells me where I want to start. For example, on this last one, I wanted to start at n equals 0. On the other ones, I wanted to start at n equals 1. So that's kind of like another idea of index. It tells you what term you want to start with. Then here we just have an expression which shows the sequence. So this is just a way of saying, here's my expression, and I'm going to substitute numbers from this number into my expression. And then my little n up here, that's what's called the upper limit of the summation, which tells me when to stop. Alright, so I'm going to start down here at I equals 1. I'm going to substitute a 1 into the equation and get a number. And then I'm going to go to a 2, and I'm going to get a sub 2. And then I'm going to put a 3 and get a sub 3. And then I'm going to go all the way up until this upper limit, and I will stop at the number that it tells me to there. So let's take a look at what this looks like with actual numbers. It's always a lot simpler when we just look at examples. So here my index is a 1, my expression is 3 times I, and my upper limit is 5. So that means that I'm going to start at 1 and put a 1 into the expression, 3 times 1. And then I'm going to add that to putting a 2 into the expression, 3 times 2. Then I'm going to add that to putting a 3 into the expression, 3 times 3. And then I'm going to put a 4 in and add that. And then I'm going to put 5 in and I'm going to add that. And then my upper limit tells me to stop. It says go all the way up until 5 and then stop. Now I would add all of these numbers together, and that would be the solution to my summation in what's called the fifth partial sum, because I'm stopping at the number 5 here. It's what's called the fifth partial sum of this sequence. So basically what I have here is 3 times 1, 3, so 3 times 15, which should just give me 45 when I add all these things together. Beautiful. Now let's look at B. My index says k equals 3. My expression right here, and my upper limit of 6. So I start at 3 this time. So I put a 3 into the equation. Boom. And I add that to putting a 4 in. Boom. Add that to putting a 5 in. Boom. Add that to putting a 6 in, and stop. My upper limit tells me to stop at 6, so that's it right there. I add all of these things together, and that would give me my partial sum, which in this case should be 90, I think. Very good. And my last one, my index down here starts at 0, my expression right here using factorials, and my upper limit of 8. And now what I do is I put a 0 in, a 1 in, a 2 in, a 3 in, a 4 in, a 5 in, a 6 in, a 7 in, 8. Beautiful, and they're all inside, and they're all going to get summed together. My upper limit told me to stop at 8, that's why I stopped there. Add them all together, and it's somewhere around 2.718. Hopefully, that isn't too complicated, but if it is, stop it for a second, write down a question, make sure that you ask me about it, we can get it figured out. Now we have a couple different properties for these sums. Some things that make things a little bit easier. For example, if I have the summation of a constant number, c is representing a constant, all I have to do there is multiply the constant by the upper limit, and that'll be my solution. I don't have to necessarily worry about going through and writing out every single term. I can do a little shortcut, multiply the constant by the upper limit. If I have a constant that's multiplying the expression, I can do a little something where I take the constant out of the summation itself and just multiply it afterwards. If I have the summation of two different expressions that are adding together, I can simply take the summation of each one separately. And once they're separately taken, add them together. Same thing is true for subtraction of two different expressions. I can take the summation of the first and simply subtract it from the summation of the second. All right, so they're very basic properties and things that you might have even thought beforehand. Alright, now let's talk about what a series is. Now, summations and series are very, very closely related. The summation is the sequence, is all of these numbers that we are adding together. And the actual action of summing all of those numbers together is what we call the series, or the partial sum. Right? So you heard me say before it was the fifth partial sum of a particular sequence. So that's also what we call a finite series, where you're taking that series and you're stopping it at a specific end value, at a specific upper limit. We also have what's called an infinite series, which is the same idea, but we don't stop it at a particular upper limit. We let it go to infinity. Okay? So we're dealing with partial sums that stop at a specific upper limit, or finite series which stop at a particular upper limit, and we deal with infinite series which go all the way to infinity. So let's take a look at this one. I want to find the third partial sum, and I also want to find the sum. So the difference between that is the third partial sum is a finite series where this value up here will be 3, and I'm stopping at 3, and the sum is simply finding the infinite series. Okay, so let's take a look at how this works. When I do the partial sum, I'm going to change up my sigma so that I have a 3 on top. I'm still going to start at 1, and my expression will still be the same, 3 over 10 to the I. And then all I have to do is start at 1, plug in values. 3 over 10 to the first, plus 3 over 10 to the second, plus 3 over 10 to the third. And that's where I stop. This is 3 over 10. This is 3 over 100. This is 3 over 1,000. When I add all those things together, that's this, and this. Boom. That is my third partial sum. Now, when I go for the infinite, this is no longer going to be a 3 up here. It's going to be an infinity. which means that I'm never going to stop. I'm going to keep going. Plus 3 over 10 to the 4th, plus 3 over 10 to the 5th. And it's going to keep going. And I'm going to keep adding 3's onto this. And 3, and 3, and 3, and 3. So what is this approaching? This is a repeating 3 that's never going to end. That's 1/3, right? 0.333 repeating is 1/3. So my infinite sum is simply approaching the value of 1/3. So that's what we do when we're trying to find the infinite sum, at least at this point. We take a look at when we add all of the terms, we continue to add the terms, what is this thing approaching? It's almost like an asymptotic relationship of the sequence of the function itself. Alrighty, and that is it for today. Please make sure that if you have any questions, you wrote them down. I will see you guys in class next time, and we'll do a whole bunch of problems together. Peace out.